Section 1.2 section 1.1 example 1.2. Write using sigma notation and evaluate. So the sum of the terms I minus 3 squared for I being 1, 2, 3, all the way up to 200. So I feel like we're kind of experts at this point at writing sigma notation. We might need to learn how to evaluate them a little bit better though. And you'll see why. Earlier we went from 1 to 5. Now we're going all the way up to 200. So we might want to learn some patterns here. So again, what we're looking at is the sum as I goes from the very first number they ask for is 1. The last number is 200. So I goes from 1 all the way to 200. And what we're evaluating is going to be I minus 3 squared. And if you really wanted to look at that, we could think of this as 1 minus 3 squared plus 2 minus 3 squared plus 3 minus 3 squared. So we could think of that all the way up to 200. Well, 200 minus 3 squared. So that would be really nice to do, but what we could actually do is break this up. If you look in the book, like a couple of parts before this problem, they had a couple of shortcuts. Well, not shortcuts, but like formulas. So the formulas that we're going to use, I'll write them once we get to it. But what I want to do is expand this, because here we have a binomial that's squared. So we could actually expand that. So let's expand it to, goes from 1 to 200. Let's do a little quick work over here. I minus 3 squared, that's I minus 3 times I minus 3. And here, here, and here, we end up with our I squared minus 6i plus 9. So that gives us I squared minus 6i plus 9. And what we could do here is we could break each of these up into its own summation. So that's going to give us the sum as I goes from 1 to 200. I squared minus, we could pull that 6 out in front. So 6 times the sum of I going from 1 to 200. I'm plus, we could leave this one on the inside just because it doesn't have any variable there. So as I goes from 1 to 200, 9. So here on this one, we have the sum. So these are going to be definitions here. The sum of, or as I goes from 1 to n of I squared, that's equal to n times n plus 1 to n plus 1 all over 6. This next one, when we have just I by itself, we have the sum as I goes from 1 to n as the sum as I goes from 1 to n of I equaling to n times our n plus 1 over 2. And lastly, when we don't have anything that we're evaluating, I going from 1 to 200 of some constant c. So in this case, that would be 9. This ends up just being n times c, and actually not 200, generalize it to n. So now we just have to replace everything with the values that we have for this problem. So here we have I going from 1 to n. I goes from 1 to 200. So everywhere we see a 200, or everywhere we see an n, we're going to plug in 200. So we have 200 times 200 plus 1 times 2 times 200 plus 1. Dividing all of that by 6. For this next part, we're still multiplying that -6. But this part here matches what we have right here. So here we have I goes from 1 to n, I goes from 1 to 200. So everywhere we see an n over here, we're going to plug in 200 as well. So 200 times 200 plus 1 all over 2. And lastly, what we have over here is we have a constant, or the sum as I goes from 1 to n, the sum as I goes from 1 to 200. So in this case, n is equal to 200. And over here we have c. So in this case, a constant is c. So we have plus that 9 times 200. Let's move this down a little bit so we have a little bit more room to work with. And now from here, I see that 6 goes into 200. We have 3 left over here. And dividing the 2's out there, we have that. 2 goes into 6 3 times. So let's try to clean this up. So here we have 100 times 200 plus 1 is 201 times 200 times 2 is 400 plus 1 is 401 divided by 3 minus here we have 200 times 201, or actually 3 times 200, 201. And lastly, we have 9 times 200, which is 1800. It looks like we could divide this here. And here we have 201 divided by 3. That's 67 here. So now we have 100 times 67 times 401, 2686700 minus here we have 3 times 200 times 201. 120600 plus 1800. So we have that number minus that number plus 1800. So our final solution, 256,900. So 2,567,900. So that is the sum of that value there. So that's the sum of what we have here of those whole numbers. And now we still have this other problem. So this one might be a little bit easier, might be a little bit tougher, who knows. The sum of the terms I cubed minus I squared for I equaling 1, 2, 3, 4, 5, 6. So these numbers are a lot smaller, a little bit more manageable. So shouldn't be too bad. Yeah, we're looking at the summation as I goes from 1 all the way up to 6. Going from 1 to 6 of I cubed minus I squared. So we could break these up into 2 different summations. The sum of I going from 1 to 6 of I cubed minus the sum of I going from 1 to 6 of I squared. So one more introduction, we have the sum as I goes from 1 to n of I cubed That's equal to n squared, n plus 1 squared over 4. And for the I squareds, we kind of remember that one from the last part. I going from 1 to n of I squared, that's n times our n plus 1 times 2n plus 1, all divided by 6. So there's those two. And now looking at this, I goes from 1 to 6, I goes from 1 to n for I cubed. So everywhere we have a 6, or everywhere we see an n here, we're going to plug in 6. So we have 6 squared times 6 plus 1 squared all over 4 minus, looking at I squareds, we have n goes from, or I goes from 1 to n, I goes from 1 to 6. So everywhere we see an n here, we're going to plug in 6. 6 times 6 plus 1, 2 times 6 plus 1, all over 6. And now let's start to factor. All right, so 6 squared, it's going to be 36 times, I know I put n, but I should have put 6 here. 6 plus 1 is 7, 7 squared is 49, and we're dividing that by 4. The 6's divide out, that's nice. So we have 7 times 6, 12, 13. There we go. We have 36 goes into 4, 9 times. So now what we have is 9 times 49 minus 7 times 13. All right, so we have 9 times 49 minus 7 times 13. That gives us 350. And there we go. That's our solution. And that's a solution to that whole problem. If you happen to have any questions, please feel free to ask. Otherwise, bye.